So, hi everyone. Thank you today for joining us for our latest webinar from Fluigent, entitled Mastering Microphysiological Precision with OMI, Automated Fluid Control for Organ-on-a-Chip Models. I'm Joseph Farah, Microfluidic Application Engineer at Fluigent, and today I'm pleased to be joined by Lucas Santin, System and Test Group Leader at Fluigent, and Arthur Sal, PhD student at the Laboratoire Interdisciplinaire des Énergies de Demain at Université Paris-Cité and CNRS.
Hello, everyone.
Hello. So let's start today with the agenda of our webinar. So we will start, first of all, by a small introduction about organ-on-chip, show you and demonstrate the opportunities, promises, and challenges for this field. Afterwards, we'll present our latest contribution in this field by introducing OMI and how it is and its capacities to mimic microphysiological conditions in organ-on-a-chip. And afterwards, we'll demonstrate and show you how it is possible to simplify your setup with the OMI. And finally, we'll have two case studies about the automation of medium recirculation with precise flow control, featuring examples of cellular gut-on-chip models with Arthur and endothelial cell culture with Lucas. So let's start, first of all, by a small introduction about the organ-on-chip. So in the last decade, organ-on-chip gained a lot of interest in the research and in the industry compared to the classical and conventional methods. So let's summarize first the conventional methods in this field and compare it to the latest advancement in organ-on-chip. So first, let's start with the 2D cell culture. As you may know, even though it is well-established methodology, it is easy to handle and quantify when you are working, for example, in Petri dishes. It is low cost. It has several disadvantages compared to the latest advancement in terms of static conditions. So basically, we are not simulating any flow, unlike what's happening in any organ, for example. The lack of similarity with the in vivo microenvironment and the large reagent volumes. If we move to the 3D cell culture or the 3D organoid, even though it improves the cell-cell interaction, it captures the 3D structure of the tissue, and it is sensitive, it's more sensitive in terms of drug treatment. It is still has some limitations in terms of the static conditions, inefficient nutrient and waste transport, and it is limited in terms of in vivo microenvironment. And so the third model is the animal model. Even though it mimics the cellular tissue microenvironment better than the 2D cell culture and the 3D cell culture, we still and there are better observations of systemic responses. It lacks a lot of it has several problems when it moves from one study to another. So we have a lot of variety in the results. There's a lot of ethical and transnational issues, expensive, and it's not disponible or it's not accessible towards all the labs. And it lacks some similarity, of course, compared to the human anatomy and physiology. During the last decades, with the emergence of microfluidics as a powerful tool in the biomedical field and even in other fields in medicine, precision medicine, and biochemistry, microfluidics presented several advantages in terms of high precision at micrometric scale, the controlled flow rate and shear stress, and improved microfabrications techniques, and high reproducibility and low reagent volumes. So basically, if we couple it, for instance, with organs dissected in smaller units, such as cells, tissue section, or organoid, we can create this thematic of organ-on-chip, where it anticipates to bridge the gap between the conventional 2D and 3D in vitro studies and the in vivo models. So the best advantages in terms of the organ-on-chips, it can be related in high control over the microenvironment, stimulate the shear stress, which is a key parameter when we are doing such studies, the possible diffusions of nutrients and drugs in a continuous way, improve the reproducibility compared to the conventional methods, and of course, the capacity of automations and integrate small analysis. During the last years, we saw a lot of or several models of organ on chip that we seeing that in the research and publications or even starting in industry. So in every type, for example, the heart on chip, kidney on chip, liver on chip, by mimicking the effects or the functionalities, by combining the microfluidics with the cells or the biological tissue of it, the gut on chip, the lung on chip, and the blood barrier, brain barrier on chip. We can summarize the chip that are actually used for these applications in 3 or 4 modes. The first one is the single channel, where you will have rectangular cross-sectional, and you will have the cells adhered on the walls. So afterwards, we can do the perfusion, recirculations, injections, and study the effect on the cells. The other types of microfluidic chips is the double channel parallel, where we'll have a porous membrane separating 2 types of cells that are adhered on the side channels of the microfluidic chip. In this case, we can do some advanced studies by comparing the 2 or mimicking more functionalities of the organ. And you have 2 types of it. For example, if you are working in a parallel mode or in a sandwich mode, if it is in the y-axis, z-axis, or the x-axis. And finally, we can combine the 3 models that we'll have, and we'll have the multi-channel. Of course, it will depend on the application. So basically, depending on the experiments, the goals, the aim that you are searching for, you can choose which model would suit you the best. The promises and the advantages of the organ on chip can lead, and like the potential targets of application will lead like the drug response, the personalized medicine, the drug screening, the disease mechanism, which can be better modelized or mimicked compared to the 2D and 3D cell culture. And in this case, the organ on chip can participate in doing or in improving the precision medicine, for example, and the process in order to study the drug and the toxicity of it and so on. However, in order to unlock all these advantages of the organ on chip, it remains some challenges in terms of instrument or how to use in order like to do the setup, to integrate it in your lab, such as the access to microfabrication facilities and expertise in order if you want to create your microfluidic chip or your microfluidic model. Less established protocols, we still don't have like a standardized way such as in 2D cell culture. And the third one, it will be the complex microfluidic setup that can be a little bit cumbersome. For example, when you are using it for the first time or you are integrating newly to your lab. For example, we can, before starting your experiment or before entering in this field or programming your microfluidic experiments in organ on chip, you will need to plan the scenario of what you are using in the microfluidic chip. For example, to do the conceptualization and design of the biological material that you are using, what material and microfluidic chip that you want to use, and the supporting life inside of the device, such as how we would like to do the perfusion, the incubator, is it compatible with it, the mechanical stimulations and control and sensors. So here I will show you in this image, for example, what, let's say, the typical microfluidic setup that would like when you are using the organ on chip applications. So you will have to choose the microfluidic chip design, if it is one membrane, for example, or one channel, or if you would like to integrate 2 membranes. Another parameter, it will be how you would like to do the perfusion or the recirculation of the cell culture media. And in this case, traditionally, we use pumps in order to create the continuous recirculation or the perfusion system. In addition, sensors can be coupled, and of course, the microscope in order to monitor what's happening inside. And like the best, it will be to have the all the system compatible with the incubator, O2, CO2, for example, if you are working in a gas environment, and the temperature. So as you can see, there's still a lot of challenges in this field in order like to guarantee and ensure the potential of organ on chip. And like the best requirements for the microfluidic circulation will be like to have microfluidic passes capable of establishing perfusion, recirculation, injection, sampling, and why not in an automated way in order to make it more practical. Have a high control and reproducibility over key parameters such as the shear stress, the flow rate, and stability, compatible with the incubator and microscopy, and compatible with if we have like a system that is compatible to any kind of microfluidic chip that can be plugged directly to your microfluidic circuit. Traditionally, in order like to do the perfusions, recirculation, you can see in the lab several processes. For example, the gravity-driven flow, tilting rocket platform, which can rotate, let's say, or recirculate the fluid from one side to another, from left to right, and vice versa. Even though it's easy to set up, you just put like the plate or the microfluidic chip, and you can do the easy setup for it. You can do an easy scale up, but it lacks a lot of control in terms of flow rate, no longer term experiments, and it's difficult to do unidirectional recirculation, which is critical when you are doing a recirculation in organ on chip. The second type, which we can see in the labs, is the syringe pumps, which is an easy setup, but it's also had a low flow plate control because of the mechanical force that we are exercising on the syringe. And in this case, you will have a lot of oscillations and noise in your flow rate, which can induce some errors in terms of your experiments afterwards. Limited volume, no recirculation, and no long-term experiments. And finally, one of for the most used in terms of recirculation processes is the peristaltic pump, where also a mechanical force will exercise some forces on the tubing and will provoke the pushing of the liquids towards the outside, and in this case, doing a loop of this system. It is easy to set up. The recirculation, you will have a recirculation loop in your system, and it can work with large volumes. However, again, with the mechanical force that is on the liquids, you will have a low reproducibility, very poor flow rate control compared to the pressure sources. So we at Fluigent, since 2006, we offer our pressure-based flow controllers and sensors, valves, and packs that can help stabilizing the flow and guarantees reproducibility when we are working in the flow rate. As you can see in this graph, compared to the syringe pumps, we will have a better response time and the responsiveness, and you will have a stability compared to the noises at the syringe pumps, especially at low, let's say, flow rates at 5 microliter per minute. How it works: the difference of pressure exercised by the pressure source and the pressure controllers will create the perfusion, let's say, or the circulation of your system of the liquids towards your microfluidic chip. We usually couple it with the flow unit in order to see to detect the flow rate and manipulate in function. We can create also some recirculation system using our pressure pumps and the valves. And as you can see, it will also guarantees the same stability in terms of the flow rate compared here in this graph to peristaltic pumps, where we see the noises and the variability of the flow rate compared to the pressure-based microfluidic control system. As you can imagine, with these types of oscillations in peristaltic pumps, it's not the best solution when you are coupled to sensitive cells, for example, and microfluidic at the micrometric scale. So in order to make it more compact, practical, automated platform dedicated for microfluidic chip, we take all our expertise a step further, and introduce the latest contribution to this field, the OMI, and its capacity to mimic microphysiological conditions in organ on chip. So in the next few slides, we'll start to discuss, we'll explain a little bit more about OMI, how it works, and its advantages compared to the microfluidic system that we already provide and the classical methods on the market. So OMI, how it works, what are the advantages? It controls the microphysiological fluid environments in organ on cell inside microfluidic chip. So we'll have a microfluidic circuit built inside the OMI, which can connect it to virtually any type of microfluidic chip, and guarantees the perfusion, injection, sampling, and recirculation towards your microfluidic chip. And it is also equipped with a remote control capacity with an application in order to automate all the processes. I will show you now a little video that describes how OMI can work. So with the OMI, you will have a cartridge, a disposable cartridge where we can inject the fluid, for example, the cell culture media. You will have 4 reservoirs, and it will be connected directly to your microfluidic chip. It fits in the incubator, it's compatible with the incubator, and you can keep the experiments running without any external pressure source of it. It is compact, you can directly see what's happening inside the microfluidic chips under classical microscopy, and it is easy to transport it from the incubator towards the hood and the microscope. Let's see now the components of the OMI. So the OMI had a touch screen interface in order to choose which microfluidic circuit you would like to introduce towards your system. You will have the 4 reservoirs, and it comes, as you can see here, in a cartridge mode that can be disposable. And it comes in a sterilized packaging in order to guarantee the stability of the system. You will have the universal adapter in order to choose which flow rate you would like, the range of flow rate that you would like to work with, and a chip holder where you can connect the microfluidic chip with it. With the OMI, you will have 4 let's say microfluidic circuits and afterwards protocols. You will have the perfusion. As you can see, you will have the microfluidic circuits built inside the OMI. RI, recirculation inlet, I, injection, O for outlet or sampling, and RO, it will be the recirculation outlet. So the perfusion, when we'll inject the media in the first reservoir in RI, and we'll exercise the flow rate, the pressure, and so on, you will have the perfusion towards your microfluidic tube, and you can recuperate it in the recirculation outlet. For the unidirectional recirculation, also which is an advantages, as it is unidirectional, you will have from recirculation outlet towards the REO, and you will have a path that can help, that will make the fluids in the reservoir all pass towards the reservoir inlet again. And in this case, we'll close the loop for your microfluidic circuit. The injection, for example, if you would like to study a drug or the molecule, you can inject it afterwards in your system. And you can do also some sampling with it without disturbing the system. You can work with the OMI in single perfusion mode or in dual perfusion mode. As you can see with the OMI, you can connect 1 microfluidic channel. And if you are interested in working in a double system, or for example with a membrane in it, you can work with the dual perfusion mode, where the OMI has a capacity of synchronization. So each OMI knows that you will have a second OMI, and the steps can be automatized and synchronized with each other. With the OMI, as mentioned, you will have a protocol that comes with the tablet that we provide and the application on it. You can set up any kind of protocols that will help you make your experiment easy here. and you can plan it in advance. For example, here we recommend to do the calibration, sterilization, loading, and afterwards you can choose what, depending on the experiments that we'd like to do, the recirculation, for example, which flow rate or shear test, the duration, and you can choose between injection, sampling, perfusion, and finally the cleaning of it. So all these steps are automatized, and you can directly plan it in the app that we provide. During the experiments, you will have a screen where you can see in real time what's happening in terms of the flow rate. You can have like a graph in order to see what in function of time, the pressure that it can reach, and the time in order to the time that is required for each step. For the recirculation, you will have, for example, the screen where you will see when the valve that is in between is open in order like to pass from recirculation outlet to the recirculation inlet and refill the system. Finally, you can see here like an example of graph that it can show after the experiments, the recirculation of, for example, if you are doing a recirculation, you can see the flow rate in function of time, and the pressure and how the pressure can automatize or like adapt itself in order to guarantee the stability of the system. And of course, each step, for example, here you can see a refill, it can be directly detectable in function of the flow rate that you are working with. So it is, you can directly monitor it in real time, the pressure, the flow rate, and so on. In order to see practically how to use the OMI, we are pleased today to have Arthur Sal from the University Paris-Cité in order to explain to us more how OMI can be adaptable or can be used in a gut-on-chip model development. Arthur.
Yes, so good morning, everyone. So now I will present to you the first case study about gut-on-chip model development. So let's start with a quick overview on what is a gut-on-chip. And especially, so the gut-on-chip models are a powerful tool for investigating the physiology and the pathology of intestines. They are small micro-engineered platforms that use microfluidic technology to recreate the structure and the functions of the human intestine, allowing more realistic in vitro studies, as presented before by Joseph. And as you can see here, so human intestine is a very complex organ with different geometry. You can find here some crypt and also some villi, and a lot of different cell types with different function. So depending on what you want to probe or to test, it exists in the literature a lot of different models, as you can see here. So if you are interested in shear stress, you will need perfusible channels and chambers, for example. Or if you're more interested in the physiology of the intestinal barrier, we'll need some 3D or 2D models with porous membrane. So in fact, the gut-on-chip models is a wide range of different microfluidic chips. And yeah, so what we wanted to apply is also to understand all the different applications. So here it is. So it's a wide range of applications from the physiology of the barrier and absorption studies and permeabilities. And you will have also the drug discovery part with the pharmacokinetic studies, the effect of chemotherapies and toxicity studies, and the whole part of the personalized medicine with also the creation of organoids from metastasis on a gut-on-chip. So in order to tackle this issue at Fluigent, we decided to use one very well-known cell type of gut-on-chip, the KCO2, derived from a colon carcinoma. So it's primarily used as a model of the intestinal epithelial barrier. And as you can see, it exists different state of differentiation of these cells. So KCO2 can spontaneously differentiate into enterocyte-like cells and exhibit many characteristics of small intestinal epithelial cells, including the formation of microvilli on the top of them, and also a more cohesive tissue, as you can see on this schema. What also is important in the literature is that the dynamic flow culture is very important for this type of cell because it will promote the cell proliferation and the differentiation. So a typical shear stress can be applied to them between 0.01 dyne per centimeter squared to 0.02 dyne per centimeter squared. So in order to tackle the issue of the shear stress and the KQ2 culture, we decided to use the B-Flow chip from Beyond Chip company, as you can see here on this picture. So in fact, B-Flow consists of two independent channels with threads, inlet and outlets, facilitating the connection to the fluidic controllers. And we decided, of course, to use OMI as the fluidic component in its recirculation mode. So as you can see, with a unidirectional flow inside the chip between the two reservoirs here. So what's the procedure when we are using OMI in this KQ2 culture? So one day before the recirculation, we are doing a seeding of the cells in a fibronectin coated B-Flow chip, and we culture it overnight at 37 degrees, 5% of CO2. The day after is the day of the starting of the recirculation. So we are doing a calibration and the sterilization of OMI. And then we are doing the connection with the chip, okay? We are pouring the medium inside the reservoir, and we set for the first day at 2 microliters per minute, which is almost 0.01 dyne per centimeter squared on shear stress. And we let the OMI in the incubator for 4 hours, and we just change the medium in order to remove the non-adherent cells from the recirculation. So here is what the tablet displayed for our protocol. So as you can see here, it's very clear to understand the different steps of the protocol from the calibration to the cleaning. You can see that the recirculation mode is split in 2 steps. So one first step at 2 microliters per minute during 2 days, and the other one is 3 microliters per minute during 5 days. So because everything is automated and it's very easy for the user to take the pictures of your chip under a microscope. So it's what we have done over time at different step points. And of course, the other task for the user is to change regularly the medium in order to have also the correct nutrients needed for the cell. So in our case, we decided to change it every 2 days, but depending on the cell types, you can change it even less time. Okay, so we set after 2 days the flow rate at 3 microliters per minute until the end at 7 days later with the last microfluidic check. So here is the microscopic views of the chip. So at time 0, we can see that there is a monolayer of cells, but a lot of cells that are not adherent to the flow of the chip. But by doing this flow, after 1 day, we can see here that the non-adherent cells are removed. And even at 2 days, we can see that the proliferation of the cells are started because, as you can see here, the cells started to colonize the ceiling of the chip after 2 days of recirculation. And after 3 days of recirculation, the whole ceiling is covered by cells here. And we can see that we have 2 different monolayers of cells inside our Beyond chip. After 7 days, the cells are still alive and in correct shape. And you can see that the cohesion of the cells is different. And in fact, if we zoom in and compare from the first day to the other 1 day here, we can see that the cell density has increased after culture under flow conditions. It exists now 3D structure formation, which is a good sign of a gut-on-chip model. And the colonization of the top of the chip, okay, after 3 days is very interesting because it's not seen under static condition with a B-flow chip. So if we sum up the Kakoto culture in OMI, affiliated with B-Flow, it's a suitable solution for long-term recirculation of cell culture media to create cellular gut-on-chip model, for example, for the shear stress effect on cells. It provides a precise flow delivery, which has allowed us to obtain a monolayer for further experimentation. And OMI is easy to use, as you can see it. It fits under any microscope. Its external footprint also is very low, so it can fit in any incubator. And with the digital app, it's a perfect companion for the on-chip biology experiments. So now I'll let my colleague Lucas present it to you as the endothelial cell culture.
Hello, everyone. Okay, so after the gut-on-chip model that was presented by Arthur, I'm going to introduce the culture of endothelial cells with OMI in order to develop a blood vessel on chip. So to develop a blood vessel on chip and more generally an organ on chip model, several parameters must be taken into account, among which there would be the biological parameters, such as the cell line that you want to use, and also the culture medium that you want to use, of course. That will depend on the cell line. There would be some chip design and surface treatment parameters, such as the microfluidic chip design and material, and the surface coating with a biomaterial, such as fibronectin, collagen, or other materials. And there is the flow control and culture microenvironment. So OMI falls in this category. It was designed to accurately generate a flow rate, which allows a precise mechanical stress and hence a relevant microenvironment for the cells. And it allows to provide fresh nutrients through medium recirculation. So in regards of developing the blood vessel on the chip, we chose to culture HUVEC cells. They stand for human umbilical vein endothelial cells. So this is one of the most common cell lines that we can find in the literature since it was first cultured in the 1970s. These cells, we use them for several reasons. They're relevant as a model, they are cheap and available, and they do not require invasive procedures as they are extracted from the umbilical cords. If we have a look at the protocol, we can notice that the material that we need is very similar to the gut-on-chip model. This is one of the strengths of using OMI and more generally organ-on-chip experiments. So the biological protocol may differ, but the fluidic protocol remains very similar. So if we go a bit deeper in the protocol, so one day before the experiment, we will coat the chip with fibronectin and then seed the cells inside and let them incubate in the incubator for 24 hours. On the D-Day, we will start by preparing OMI, doing a calibration, a sterilization, and a loading of the culture medium that we're going to use in the experiment. This will allow to remove any air bubble from the fluidic line inside the OMI. Then we will connect the chip and set the flow rate that we want. That's where actually the protocol differs from the gut-on-chip model, apart from the biological parameters. Here we set two recirculation parameters of 10 and 500 microliter per minute, which will allow one small shear stress and one high shear stress. And then we place the OMI in the incubator, and on a regular basis, like 24 to 48 hours or even 72 hours, we will change the medium, which will remove the non-adherent cells from the recirculation and also bring fresh medium to bring fresh nutrients to the cells. So very quickly, because you already saw that in the previous case study, this is the protocol we use. So this is very simple. There's just one recirculation step at either 10 or 500 microliter per minute for 7 days. And we have the typical calibration, sterilization, loading, and cleaning steps that are required for the experiments. Yeah, here you can see the flow rate of 500 microliter per minute. Okay, so After 1 day of experiment, we check that the cells are still still in shape, and we check if we start to observe some difference in terms of cell physiology, and then we will, as I mentioned, change the medium and restart the experiment, and we will do it at day +1, day +3, and day +5. And then on the last day, we remove OMI from the incubator and we observe the cell morphology under microscope. Here, we can, with OMI, monitor the flow rate in real time. As you can see here, there are two graphs, one at 10 microliter per minute and the other one at 500 microliter per minute. It shows excellent flow rate stability. Concerning the low flow rate, we used a high resistance adapter to have a high fluidic resistance and allow for more precision at small flow rate. And for the 500 microliter per minute, which is quite a high flow rate, we use a low resistance adapter. Okay, so after 7 days with under OMI recirculation, at 10 microliter per minute, we can see that the cells remain viable, but we cannot observe major changes in cellular morphology. It looks a bit cleaner, so some of the dead cells were removed, some debris were removed, but the cell morphology remains the same. Whereas at 500 microliter per minute, we can see that the cells started to elongate, and they are starting to follow some patterns, and they start to get oriented alongside the flow. Okay, so now something that we saw by recirculating with OMI as well is that first you start with a monolayer of cells on your bottom line of the chip, and then after several days you start to see when you change the focus that the cells are starting to migrate towards the upper side of the chip through the walls. And if you wait for 1 week, 2 weeks, you will end up with a complete blood vessel with all the walls covered with cells. So in a nutshell, what we saw here with OMI is that it is a suitable solution for long-term recirculation of cells under in a microfluidic chip. It allows us to create a physiologically more relevant blood vessel than classical methods. And it can be seen by the fact that cells tend to elongate with the flow rate, and also that they start to spread all over the chip to form a real blood vessel. And also, we could see that the flow rate delivered with OMI is very stable and very precise, which allows us to really control our fluidic parameters in our experiments.
Thank you, Luca, and Arthur for these two case studies, which illustrates the advantages of OMI. So just to summarize at the end of this webinar, as you can see, the organ-on-chip field is quite promising in terms of the advantages compared to the conventional methods that are already existing in this field, such as the 2-cell, the 2D cell culture, and so on. OMI, in order to guarantee or to provide these advantages, you will need a microfluidic system that is able to guarantee these advantages, and the OMI will have the versatility, a reduced contamination, a gain in productivity with the automation, and the reduced interoperator variability. Plus, it is compact and autonomous. So we hope by the end, by the end of this webinar, that we provided some new insights about the organ-on-chip experiments, that you can use it afterwards in your microfluidic in your applications. So I would like first to thank you for your time today for this webinar, and stay tuned for the upcoming webinars with Fluigent. Have a nice day.
Thank you. Have a nice day.
Thank you. Bye.